Example 5. In this example, we are going to analyze the graph of f of x is equal to x minus 2 over x squared minus x minus 2. Now, the first thing I'd want to do is factor the bottom of this function. So I have f of x is equal to, and the top is just an x, so that can't be factored, but the bottom can. So I need an x and an x. Notice here that I need factors of negative 2 that will add to give me negative 1, and that would be negative 2 and positive 1. Just to do a quick check, negative 2x, if you do inside times inside, plus 1x would give you negative x. And of course, x times x is x squared. Negative 2 times 1 is negative 2. So that is the factored form of my rational function. All right, so now I'm going to find the domain. Remember, to find the domain, you're going to set the denominator equal or not equal to 0. So I'm going to have x minus 2 times x plus 1 does not equal 0. So x minus 2 cannot equal 0. So x cannot equal 2. X plus 1 cannot equal 0. So x cannot equal negative 1. Because remember, when you're finding domain, you're finding the numbers that will make this function undefined, and you're pulling those out of the set of real numbers. And since 2 and negative 1 make the denominator 0, the function would be undefined there. So my domain is going to be from negative infinity up to negative 1, union negative 1 to 2, union 2 to infinity. I think it didn't write my 1 there. All right. Now to find your x and y intercepts. So remember, to find your x-intercepts, you're going to let y equal 0. And for a rational function, you can just set the numerator equal to 0. So I have x minus 2 is equal to 0, so x is equal to 2. You always need to check your x-intercepts against your domain. And look, I got 2 as an intercept. However, 2 makes the bottom 0. So I cannot use this x-intercepts because it's not in the domain. So there are no x-intercepts. To find the y-intercepts, you're going to let x equal 0. And again, I like to do that in the unfactored form because anything with an x in it is going to go away. So I just have negative 2 over negative 2 because all these would be 0. So y is equal to negative 2 over negative 2 or 1. So I do have one intercept, and that would be at 0, 1. All right. So now we're going to holes. Remember, holes go hand in hand with the domain. And so do vertical asymptotes. So we have two numbers that x can't be. One of them, there's going to be a hole, and the other one, there's going to be a vertical asymptote. So if we look up here, we notice that we have x minus 2 in the top and the bottom. Because we have this common factor in the top and the bottom, that means there will be a hole in this graph. Instead of a vertical asymptote. All right. So we're going to have a hole when x is equal to, well, let's see, we're going to take that x minus 2, and that would give us x equals 2. So our x-coordinate of the hole is 2. To find the y-coordinate, remember you're going to plug your x value into the simplified function. So plug x into simplified function. So I had f of x is equal to x minus 2 over x minus 2 times x plus 1. So my x minus 2's cancel, but it doesn't leave nothing up here. You can't say that f of x is just equal to x plus 1 because x plus 1 is in the denominator. So remember, when things cancel out in a fraction, they cancel out to 1. So the simplified version of this function would be 1 over x plus 1. So now to find the y-coordinate, you're going to find f of 2 in this simplified version, and that's going to give us 1 over 2 plus 1, or 3. So our whole is going to be, at the ordered pair, 2 1/3. So when we get to that point, we're going to graph an open circle there. All right, so we know we have a vertical asymptote as well, and that's going to be at x equals -1. Because that's the other factor in the denominator that causes, that doesn't have a common factor at the top. So we have a hole here, vertical asymptote there. All right, and then finally horizontal or slant. Well, let's see. The degree on the top is 1. The degree on the bottom is 2, so this is another bottom heavy function, which means the horizontal asymptote is automatically y equals 0. Because if it's bottom heavy, it's going to pull me down to sit on the x-axis. All right, so let's graph what we do know. So we have a vertical asymptote at x equals -1. So I'm going to draw a dashed line there. So this is a vertical asymptote at x equals -1. I have a hole at 2 1/3. So I'm going to go to 1, 2, and up 1/3, and I'm going to graph an open circle. So that's going to be a hole at 2 1/3. And then I have a horizontal asymptote on the y-axis again. I'm sorry, on the x-axis, not the y. Sorry about that. And notice that your asymptotes are always y equals or x equals something. You just don't say 0 because it's not a number, it's a line. So the line needs a letter with it. And then I did have one point on this graph, and that's the point 0, 1. So I can go ahead and plot that point here. All right, so let's see. So I kind of know what's going on this side. So it looks like the graph is going to come up here, and then it's going to go through the hole and come down here. But I need a couple points over here. So I used a few points to the left of -1. So I used -2, -3, and -3/2. And when I plugged in -2, I got -1. When I plugged in -3, I got -1/2. And I plugged in -3/2, I got -2. So -2 -1, -3, -1/2, and then -1.5, I got -2. So it looks like on this side, we're going to come up here and then go down here. So I'm really trying to model what I want to see on a test. Notice that I have labeled my asymptotes, labeled my hole. I have 3 points over here. If you count the hole as kind of one of your guiding points to graph, you have 2 over here. You could pick one other point and plug it into the function. Let's use x equals 1. So if I find f of 1, that's going to give me 1 minus 2 over 1 minus 2 times 1 plus 1. So that's going to give me -1 over -1 times 2, right? -1 times 2, which would give me a positive 1/2. And there's that point right there, 1/1/2. You could pick points out here to help justify it coming closer and closer to the x-axis. And that's the graph.